In this lesson, we shall focus on complex numbers. Right now, complex numbers remain very, very important in this section, in this module, and are examinable. And let's get started with looking at some concepts pertaining complex numbers. Right, we need to be able to express, or in particular, deal with and solve exercise 5. Express the following complex numbers in polar form. Right. For example, in A, we need to be able to express the complex number Z, the complex number 1 plus I in polar form. And to express the complex number in polar form, we actually position 1 and we position I, and then we plot the number like so. And we put this angle, we call it theta. We take the tan of theta, we call it y over x. And the tangent of the y, the number is of the form x plus iy. That is the form. So the x here, the y is 1, which is 1. And therefore, if tan theta is 1, arctan 1, which is equal to pi over 4. And obviously, this gives us the square root of 2 as well, using Pythagoras theorem, and this angle becomes pi over 4 radians. So that this is r plus I sine theta. Okay, r becomes the modulus of the number, which is 1 squared plus 1 squared, which is the square root of 2. And then you have the cosine of pi over 4, I the sine of pi over 4. So this is the expression in polar form. Any question about the polar form? Any question about the polar form? Make sure you understand this, because it's very easy and it's something you need to understand. Obviously, now if z is x plus iy, this then means the modulus. The modulus of z, okay, I'm checking the charts. Okay, when did we get to trig? Okay, that's the thing, because always if you have a complex number, there's a formula we use. Right, there's a formula we use. X plus iy is r cosine theta plus I sine theta. This is the formula. So this is equal to this. The rectangular form is equal to the polar form. So now when given x plus iy, you must find its modulus. X plus iy, find the modulus, and therefore the modulus of x plus iy, this modulus becomes the square root of x squared plus y squared. So now you find the modulus of the 1 plus I, which is 1 squared plus 1 squared, which is the square root of 2. So you put out the radius, which is square root of 2, and then the angle theta, this angle. How do you get the angle theta? You actually take the tangent of theta, which is y over x, and then it is 1 over 1. And then if tan theta is 1, then theta is arctan 1, and arctan 1 is pi over 4 radians. So given a complex number in rectangular form, these are all in rectangular form, you can write it in trigonometric form, or you can write it in what we call the polar form. The polar form. Let us try the next question. The next one is B, which is the imaginary z, the real z. X is minus 1, y is 1. Right, so it's r squared. So the x is minus 1 squared plus 1 squared is r squared, which means r becomes the square root of 2. Given minus 1 plus I, the formula is you can always write it as r cosine theta plus I sine theta. By the Pythagoras theorem, what is the radius? The radius is the square root of 2 units. The angle theta. Now, if you do, the tan is y over x. The y is 1, the x is minus 1, which means the tan of theta is minus 1. And theta is arctan of minus 1. And arctan of minus 1 is equal to what? It's equal to minus pi over 3. But since this angle is positive, then you must say theta is pi minus pi over 3. Okay? If an angle is negative, then you must do that. So obviously, let me do it very well. Okay, like when we are in school, we do the reference angles, so you can do the reference angles here. So now in this case, you find the tan of theta equals that. So you take this one. So you're going to have tan theta equals 1. And then now you find so for the reference angle, you take theta equals 1. Pi over 4. So that now the theta becomes pi minus pi over 4. And then this is 3 pi over 4 radians. So we put here 3 pi over 4 I, the sine of 3 pi over 4 radians, which is minus 1 plus I. So it is the answer they've got there. Any question about this? So this angle would be 3 pi over 4 radians. So the formula is that given in rectangular form, you can write it as r in brackets cosine theta plus I sine theta. The radius becomes the square root of 2. The angle becomes 3 pi over 4 radians. Make sure you understand converting from a trigonometric, from the rectangular form to a polar form. Make sure that you understand that. And that you understand this very, very well. Let's move on to the next question. Part C. So you have the imaginary Z and then we have the real Z. And therefore you have I. I always you can write it as the radius cosine theta plus I sine theta. So by Pythagoras theorem, then you must be able to do x squared plus y squared is the radius squared. So if the number is like this, it's just I is 0 plus 1 times I. So that this is x and that is y. X is 0 squared, the y is 1 squared is equal to r squared. Okay, now to explain this one is the Cartesian plane. So in the Cartesian plane, what you do, you plot the complex numbers so that you can be able to see the angle. Right. So, so we continue. So now you have x squared plus y squared is equal to r squared. So now then this is the case. so that this is the diagram. You plot the number, because this I, you put it here on the y-axis, and the x, you put it on the horizontal axis. But obviously, if it's just I, then it means that like it's y equals 1, because this I is 1I, and the complex number is x plus yi. So which means that for if it's just I, then y is 1. And then now we're going to find the angle here. The angles are always pretty much measured in a counterclockwise direction. So you go against the clock. And this angle is pi over 2 radians. Therefore, the r, if 1 is r squared, it means if we can get the square root of 1, the square root of r squared, which means r is 1. You put 1 cosine. Now, this is called the Argand diagram. Argand diagram. So the angle theta therefore becomes what? Becomes pi over 2 plus I, the sine of pi over 2. Right, and therefore this is the answer. So we have converted I to what we call the polar form. What is the formula for converting? So it is the polar form, or what we call the trigonometric form. It's called the trigonometric form. So the radius, you must get the radius. How to get the radius given in a complex number in rectangular form? All these numbers are given what you want to call rectangular form. In rectangular form. Right. So we continue. We continue. Any question about this rectangular form? So you must be able to convert the rectangular form to a polar form. And also you must be able to convert a polar form back to a rectangular form. So use a calculator for that, because like cosine pi over 2 is like cosine 90, which is 0. The sine of 90 is 1. So that this whole thing is maintained there. So that this whole thing is maintained there. So that is it. That is it exactly. That is it exactly. That is it exactly. We continue. So let us look at the next one. Like now we were doing C. Let us do D. D is this one. So first you must draw what you call your Argand diagram first. Argand diagram. And then we have minus I. And then this is the vertical axis is called the imaginary axis, and this is called the real axis of Z. Real Z. Imaginary Z. So now you're gonna measure so there are two possible angles here. If you measure like this is 90 degrees, but now it's gonna be minus pi over 2 radians. Or you go like this. If you go like this one is 0, pi over 2, Yeah, it's y, because now if you plot a complex number x plus iy, this complex number x is here. X is somewhere and y is there. So if you plot this complex number, you find that x is there and y is here. So you can put yi here. So that this is the complex number. This is how we plot a complex number. This is the complex number x plus iy, like that. You get the point. Right. You continue. So that then in the end, what you're having here, what you're then having here becomes the following. So now let us look at the complex number minus I. The formula we're going to use is R cosine theta plus I sine theta. But also you can use R e to the I theta, which is called Euler's formula. You can use what we call Euler's formula. Euler's formula. Which means you have minus I. What is the radius? To find R, use R squared is x squared plus y squared. Zero minus I. Zero squared minus that squared. So R equals 1. By Pythagoras theorem. Then what is the angle theta? This is the angle theta. So the angle theta is minus pi over 2. Plus I, the sine of minus pi over 2. The R is 1 e to the I minus pi over 2. Any question about this? And therefore, this is the angle. But now, you can write 3 pi over 2, but this is minus 90 degrees. But if you go like this, counterclockwise, then it is 3 pi over 2 radians. So you can write like that, or you can say the minus I is 1, the radius, cosine, the angle. You can take minus pi over 2, or you can measure 3 pi over 2 radians. Plus I, the sine of 3 pi over 2 radians. Which is this one. Which is exactly this one here. For part D. Any question about this? Any question about this? Right. So any question about this? Make sure you understand this. This diagram, you just plot the complex number. If they've given you minus I, then the complex number, y is negative 1. So this thing is 0 minus I. You must always have a real number there. So x is 0, which is the origin. And then y is minus I there. So we continue. We continue. All right. So we continue. Any question about this? So if the I is this one, the minus I is this one, the vertical axis is called the imaginary axis. This is called the real axis. So this angle is pi over 2 radians, negative. And this one is 3 pi over 2 radians. So we continue. We continue. We continue. Right, let's look at the letter E. 2 plus I, 2 to the square root of 3. Okay. Imagine that real Z. This one is 2 plus that. So 2 plus that, this is 2. This is like X and this is Y. IY. So X is 2 and then Y is 2 to the square root of 3. It is this one. So you're going to form this triangle here. The tan theta is Y over X, and Y is 2 to the square root of 3 over X, which is 2. Which is the square root of 3 arctan the square root of 3. Opposite over adjacent. So facial triangles, if this is the square root of 3, 1, 2, pi over 6, pi of 3. So this is SOHCAHTOA. SOHCAHTOA. So that the tangent is opposite over adjacent, pi over 3. Opposite over adjacent. So if this is arctan, the tangent of this is pi over 3, so this angle is pi over 3 radians. Right. And so now you need to use Pythagoras. X squared plus Y squared is R squared. X is 2. 2 squared. The Y is 2 to the square root of 3. Is R squared, which is 4 plus 4 by 3, 12. 16. Square root, which means 4 is R. Which means that you have 2 plus I, 2 to the square root of 3, which is R cosine theta plus I sine theta. R is 4. And the angle theta we've already seen is exactly pi over 3 measured in a counterclockwise direction. Plus I, the sine of pi over 3. So we have this. We have this exactly. Any question about this? Think about it and make sure you understand. What is the formula? The formula is that given any complex number in the rectangular form, you can write R in brackets cosine theta plus I sine theta. Always you can do this. Always you can do this. So now think about it and make sure you understand this. Make sure you understand this. So we continue. We continue. Right, so okay, think about it and make sure you understand it. Right, so we continue. We continue. We continue. So we continue. Any question? Any question? Right, in absence of a question, we move on to try the next one, which is F. Right, to deal with F, let us draw our Gantt diagram. So we have -6 minus I the square root of 2. Because minus the square root of 6 is this one. X is negative here because we're looking at the number minus the complex number minus the square root of 6 minus I the square root of 2. Imaginary Z and real Z. Minus the square root of 6 and then minus I the square root of 2, so you have this number. So there are two things that. So now we consider positive angles. So angles are measured in a counterclockwise direction. So this is the angle. Right. So you have the tangent of theta, which is y over x. Y is minus square root of 2, x is minus square root of 6. One over the square root of 3. Which is I sine theta. So now x squared plus y squared is equal to r squared is Pythagoras theorem. The x is this one, and the y is that. So you have the x minus square root of 6, you square it. The y is minus square root of 2, you square it, is r squared, which is 6 plus 2, r squared is 8. The square root of 8, the square root of r squared, which means r is the square root of 8. But the square root of 8, you can also write it in many ways. The square root of 8, 8 is 4 times 2. The square root of 4 is 2, the square root of 2 equals r. 2, the square root of 2. That's the square root of 8. And therefore, cosine of the angle. The question is, what is this angle? So if you have this, then you're going to use the special triangles. Right, if this is pi out of 6, this is pi out of 3. Pi out of 3, 1, 2, 1. So the angle theta. So now if you look at this, then the angle theta would be, so if you have 1 over the square root of 3, then it is actually exactly opposite of adjacent, which is pi out of 6. This is pi out of 6. Right, pi out of 6, then this one is pi. So you take pi plus pi out of 6, which is 7 pi out of 6. So you're going to do 7 pi out of 6. Okay. So we continue. We continue. So that you have plus I, the sine of 7 pi out of 6. And then which is exactly this one. So now we're going to try G, this one, because I'm also write it in what? In polar form. All right. So then now you have this one, which is 2 plus the square root of 3. So we continue. And then this one is 2 minus the square root of 3. So we plot it here. This is the x and this is the y. What is the angle here? In the Argand diagram, this is imaginary z and this one is real z. So write the tan of theta is y over x. The tan of theta, the y, the square root of 2 minus square root of 3. The x is the square root of 2 plus the square root of 3. Which is the square root of 2 minus square root of 3 divided by 2 plus square root of 3. So the tangent of theta will actually exactly be this. So this you're going to rationalize and have 2 minus square root of 3, 2 minus square root of 3 under the square root, which is 4 minus 3, 4, 2 minus, yeah? So we're going to have this one, which is the tan of theta, 2 minus square root of 3 squared divided by 4 minus 3. Which is 1 in the denominator, and the top you take the square root of it, which is exactly 2 minus the square root of 3. Right, what is the angle? So when you're going to do x squared plus y squared is r squared. The x is the square root. The y is the square root. And therefore, this is 2 plus square root of 3. 2 minus square root of 3 is r squared. 4 is equal to r squared, which means therefore you can take the square root of 4, the square root of r squared. R is 2. 2 plus square root of 3. 2 minus square root of 3. Cosine theta plus I sine theta. The R is 2, the cosine of the angle theta. So now we need to use a calculator. So to get the angle theta, then you're going to do theta is arctan of 2 minus the square root of 3. So we continue. arctan 2 minus square root of 3. Which is exactly 15 degrees. 15 degrees. Now the 15 degrees is pi out of 12. Because if you do 180 degrees divided by 12, it's 15 degrees. So it's pi out of 12. So right here, you're going to come here and put pi out of 12. Pi out of 12. So this is it. This is the answer. This is the answer. Any question about this? Any question about this? So this one is the radius is 2. This is r in g cosine theta plus I the sine of theta. Okay, that is the Argand diagram there. And the complex number is this one. The angle theta is pi out of 12, which is the same as 15 degrees. Okay. Let us see what else we can do. There's something called the Moivre's theorem. Right, this is the Moivre's theorem. What is the Moivre's theorem? The Moivre. So the Moivre's theorem means that when you have the cosine of phi plus I the sine of phi, you raise it to n, it is cosine n phi plus I the sine of n phi. Okay. So this is called the Moivre's theorem. Let us see, and it's been stated here in the material. So, but now we can practice with the Moivre's theorem. Like if you're gonna do cosine phi plus I sine phi, and then you square it, it is cosine of 2 phi plus I sine phi. Cosine of phi plus I sine phi, you cube it. Cosine of 3 phi plus I, the sine of 3 phi. Cosine of phi I sine phi, you raise it to the fourth power. For phi plus I sine phi. We continue. We continue. Let us look at some other things we can do with the Moivre. Now with the Moivre, we need to calculate, like they're saying calculate 1 plus I to the power 24. But to calculate this, we must first write this number in so you add that, 1 plus I, and then you plot it. So that the tan of theta is y over x. Tan of theta is 1. Then here you're going to use your arctan 1 pi over 4. So now the number, start with the number 1 plus I. r cosine theta plus I sine theta. The r is the square root of 2. So this is the square root of 2. The cosine of this angle is pi over 4 radians. And then you can form a triangle like this. Pi over 4, I, the sine of pi over 4. 1 plus I to 24, which is the square root of 2 to 24. The cosine of pi over 4 plus I, the sine of pi over 4. 1 plus I to 24. This one, the square root is 2 to the power 1/2, and then you take half of half of 24 is 2 to the power 12. This 24 by De Moivre's theorem is going to multiply the angle, giving us cosine of 24 pi over 4, the sine of 24 pi over 4, which is cosine of this. 24 divided by 4 is 6 pi plus I, this I is 6 pi. Right, so what is 6 pi? Obviously 2 to the 12 is part of it. You'd have like a 2 to the 12. 2 to the 12. So this one is going to be exactly 2 to the 12. And this is 1 plus 0i. And then 2 to the 12, you can use a calculator. Let's just use a calculator for that one. All right, so you have 2 to the power 12, which is 4096. 4096. Okay, let's see what you have. So that is the example. Yes, so the square root of 2 is r. The square root of 2 is r, which you can put here. R11. Okay. And this is a right angle triangle like this. Any question there? Any question? Think about it and make sure you understand this, because now we're going to move to the next problem. Okay, let's see what we have here now. Let us see what we have here now. So let us look at this one. We're looking at, this was just an example. This example uses De Moivre's theorem. At this step here, it is De Moivre. So at this step here, it is De Moivre. At this step here, it is De Moivre. We have said before that De Moivre is this step here. This is De Moivre. That becomes De Moivre. So think about it and make sure you understand it. Let us continue with our analysis of the problems. Okay, I want us to look at the next question. And for example, if you look at this example, it is still Moivre, but the way it has been given is very, very mixed up. It is so disguised that it has many, it doesn't have a very direct look. But you need to do a couple of things to deal with it. You need to first rationalize. Given that equals 4i divided by the square root of 3 minus i. 4i divided by the square root of 3 minus i. So you multiply by the square root of 3 plus i, square root of 3 plus i. And this is 3 plus 1. We multiply here, which becomes 4 the square root of 3i minus 4. We divide by 4. 4 the square root of 3i out of 4, which is exactly the square root of 3i minus 1. And this is the complex number. So given this complex number, this one is the same as the square root of 3i minus 1. But you can write it as what? You can write it as minus 1 square root of 3i, which is x is minus 1, y the square root of 3i. So it's the number that sits here. So that in the end, then you have this complex, you have this argument. So this you're going to use tan theta is y over x. Y is the square root of 3, x is minus 1. So which means theta now opposite the square root of 3. Square root of 3 to 1, this part of 6, part of 3. Okay. Now at this point, you must first write this complex number. So in other words, z, which is equal to 4i divided by the square root of 3 minus I, is minus 1 plus the square root of 3i. What is the modulus of this number? Must get the modulus. So the modulus of z is the modulus of minus 1 plus the square root of 3i, which is the square root of minus 1 squared plus the square root of 3 squared, which is 3 plus 1, 4. Square root of 4, 2. R is 2. So if you write this complex number, it is r cosine theta plus I sine theta. What is the radius? It's 2. And the angle theta is pi over 3. This is 2 pi over 3. Plus I, the sine of 2 pi over 3. So we continue. That is the answer there. And that is the answer. And that becomes the answer. Any question? Oh, we must raise it to a power. We need to raise it to a power. So you're going to have, if this is the case, then you need to raise it to the power 6. So you'd have 2, the cosine of 2 pi over 3, plus I, the sine of 2 pi over 3. which is 2 to the power 6. The cosine of 6 by that, which is 12 pi out of 3 plus I, the sine of 12 pi out of 3. 2 to the power 6. You divide by this, which is the cosine of 12 divided by 3 is 4. 4 pi plus I, the sine of 4 pi. And then the 4 pi is 1. So we continue. Any question? Because now 2 to the power 6 is the same as 64 here. 2 to the power 6 is the same as what? 64. 2 to the power 6 is the same as 64. All right, so now this is the answer, but obviously we're just doing this example just to make sure we understand it. But obviously we're getting the same answer, which is 64. Z to the power 6 is 64. The first thing is to convert the number which is given the form in rectangular form to polar form and then use the Moivre's theorem. The Moivre's theorem says when you raise to the power, you must multiply the angle and you must raise the radius to the power. So we raise 2 to the power 6 and then multiply the angle by 6. Okay. So now this one is exactly what we've done. That's exactly what we have done. Now let us look at the next problem. Now, given a complex number, we can be able to extract something called the real part of it, and also we can be able to get the imaginary part of it. So now, in this example, let's just look at exercise 6. Now you need to express 5 theta in terms of theta. So this is the answer. Ready? But to express 5 theta in terms of theta, you write the following. You write cosine theta plus I sine theta. Okay. And you can first write it as this. Cosine 5 theta plus I sine theta. You raise it to that. So if we continue with the multiplication, then what do we get out of this? If you raise this to the power 5, use Pascal's triangle. Right, Pascal's triangle is clear that when you put 1, 1, then you get 2, 1, 1. 3, 3, 1, 1. 4, 6, 4, 1, 1. 5, 10, 10, 5, 1, 1. So we're going to have this one, the coefficients. So it's going to be cosine to the power 5 of theta. Then you put 5 cosine to the power 4 of theta, which is I sine theta. So we continue. So which is cosine 5 theta. Okay, by the Pascal's triangle, then you're going to have exactly that. Right. So we continue. Now this is cosine to the power 4 of theta. Then we have I sine theta. cosine to the power 3 of theta. Yeah, it stands for the real part. So if you see R like this, stands for the real part. If Z is X plus IY, then if you do real part of Z, the real part of Z is X. And the imaginary part of Z is Y. Okay. So something that you take note of there. Okay, so let us practice together. Starting from the margin. Yeah, so they've taken a real part of that. Because if you take the real part of this, is that, yeah, that's correct. Because now it's when you take, if you take cosine n theta, I the sine of n theta. This is cosine theta plus I sine theta. And this means that you have the real part plus I sine theta. Now, the real part, you must take this one. So the real part of this big thing, because this big thing is equal to this. So the real part, these things are equal because of Moivre. Moivre says that this n multiplies the angle. So that is cosine n theta, and then it is I sine n theta. But if you take the real part of this big thing, then it is the same as cosine n theta. Then if you take the imaginary part of this big thing, the imaginary part becomes the sine of n theta. So the imaginary part is the coefficient of the I. That is why the imaginary part is the sine n theta, but the real part is cosine n theta. Okay. So obviously we're going to just practice with it now because it's the same thing that they asked us. So we have this. Now, we want to consider this now. You raise it to the power 5. If you raise it to the power 5, it becomes the cosine of 5 theta. By Pascal's triangle, then you put 5. And then you have I sine n theta. You have I sine theta. And then now you have this one cube and this one is squared. With a 10. 10. Okay, this is called the binomial theorem. So this is 4, is 5, 4, 3, 2, 1. So when this is 5, this is 4. And then this one is increasing by 1 because it was not here, it was not there, here it was 0. Then it's 1 here, it's 2, 3, and so on. So this one is going to be a square. And then you cube it. Plus 5 cosine theta I sine theta to the 4th power. I sine theta to the 5th power. So which means which is 5I cosine 4 theta, the sine of theta, which is, and then this is minus 10I cosine squared sine cube theta. Then this is positive plus 5 cosine theta, the sine to the power 4 theta. And this is plus I, the sine to the power 5 of theta. So now at this point, you just expand this and multiply to the power 5, but it's easier to use the binomial theorem where the powers increase 5, then it is in this order. So now you have real, no I, there's I, no I, no I, which means cosine to the power 5 of theta minus 10 cosine cubed of theta sine theta, which means plus 5 cosine theta sine to the power 4 of theta. Plus I. Cosine to the power 4 of theta sine theta minus 10 cosine squared of theta sine cubed theta plus the sine to the power 5 of theta. So these things here, this cosine 5 theta is equal to this, which means that cosine 5 theta is exactly equal to this, which is cosine to the power 5 of theta minus 10 cosine cubed sine theta plus 5 cosine theta, the sine to the power 4 of theta. Then you must simplify this and put some other things because it must be exactly this. So which means that whenever the sine is there to the 4th power, then you can perform some changes. Because this one you can see is in terms of cosine only, so you must remove every sine that is there. All right, to remove every sine that is there, you must proceed as follows. Because we have this, you have exactly that. So if you check very carefully, you have this one. Let me see what you have here. Okay. Yeah, so this is the squared. Squared from there, squared there, squared there. Okay, now this one is the answer part. If you have cosine 5 theta is equal to cosine to the power 5 of theta minus 10 cosine cubed, and then sine squared theta plus 5 cosine theta sine to the power 4 of theta, which means cosine 5 of theta, which is 10 cosine that. So we know from high school that cosine squared theta plus sine squared theta. So, I mean, what we're saying here is therefore that if you're taking the real part of cosine theta plus I sine theta to the power 5, the real part of this is just what? The real part is just cosine 5 theta. That is the real part. Right. So we come here. This is 1, which is 1 minus cosine squared theta, which is 5 cosine theta sine squared squared. which is minus 10 cosine cubed theta, 10 cosine to the power 5 of theta. Right. 5 cosine theta. The sine squared is 1 minus cosine squared. And then you have a square there, which means this is the same as cosine to the power 5 of theta minus 10 cosine cubed of theta, 10 cosine to the power 5 of theta. Okay, if you square this one, it becomes 5 cosine theta. And then it becomes minus 2 of this, which is minus 10 cosine cubed theta. And then to the 4th power plus 5 cosine to the 5th power of theta, which means cosine this to the 5th power to the 5th power, or to the 5th power, and then 10 of this is 11 plus 5 is 16. So you have 16 cosine to the 5th power of theta. We're done with this, and that. Then you have the 10 cubed, the cubed. The cubed minus 10 is actually minus 20 cosine cubed theta plus 5 cosine theta. Then now you would actually therefore take the following. Now, if you're dealing with if this is de Moivre, okay, de Moivre is written with small d, not what they wrote in your material there. But it's something called de Moivre theorem. So de Moivre theorem would be when you have this cosine theta plus I sine theta. Cosine theta plus I sine theta, you raise it to the power 5. It is cosine 5 theta plus I, the sine of 5 theta. So if you take the real part of cosine theta plus I, the sine of theta, you take the real part of this, which is cosine 5 theta. But if you take the imaginary part, okay, the imaginary part becomes the sine. So you can take the real part of everything. So if you take the real part of this thing, it's equal to that, which is the real part. Right, the real part. And then this im stands for the imaginary part. The imaginary part. Okay, so we've proven this one now. We've expressed cosine 5 theta in terms of cosine theta. You can see that the answer is in terms of cosine theta. But first, when we got this cosine 5 theta, it was in terms of cosine and sine theta. But now we have removed all the sine, then we have everything in terms of cosine theta there. Okay, look at it and think about it very carefully. All right, look at it and think about it very carefully. Let us continue and try more problems. Okay, show that this is the case. So we can practice with these ones. So because these ones are 2, it's the same thing. But here you have the cosine 4 and sine 4. So you are supposed to have cosine 4 I sine 4 theta. cosine 4, which is I sine theta. You raise it to the fourth by Pascal's triangle. Pascal's triangle says 1, 1. 1 plus 1 is 2. 3. 2 plus 1, 3. 1, 1. 4, 6, 4, 1, 1. So if you raise it to the fourth power, right, so it is the same as what? Which is the same as we continue. It becomes 4 cosine cube theta. I the sine of theta. 6 cosine squared theta. I sine theta squared. Plus 4, the powers is 3, 2, it decreases by 1, the other one is increasing by 1. But the coefficients are these from the Pascal's triangle. Then you're going to have the 4, which is going to be cosine theta I sine cubed. And then plus I, the sine of theta to the fourth power. Which is 4 cosine cubed theta sine theta. Which is sine theta. And then we have the sine to the power 4 of theta. So which means that which is sine theta sine to the power 4 of theta. Cube theta sine theta. Minus 4 cosine theta, the sine cubed of theta. Right. So now, which means that if you check the real part, the cosine 4 theta is equal to this. Cosine 4 theta is cosine to the power 4 of theta minus 6 cosine cubed theta sine theta plus the sine to the power 4 of theta. Okay. But you can see that this one is written only in terms of, it's okay that it's x theta, it's the same thing. You can change theta to x. But this one now is in terms of, it must be in terms of, you must change the cosine to sine. Change the cosine to sine because everything here is in terms of sine. So you can do this. But if you have this, it is cosine squared theta squared. Okay. And then you can do cosine squared theta. Then this is cosine theta sine theta. Sine to the power 4 of theta. So which means that now if you go to Sine squared theta plus cosine squared theta is equal to 1. Cosine squared is 1 minus sine squared theta. 1 minus sine squared theta squared. Minus 6. The cosine squared is 1 minus sine squared theta. Cosine theta sine theta plus the sine to the power 4 of theta, which is 1 minus 2 sine squared theta plus the sine to the power 4 of theta. Okay. So we can just use the identities to manipulate this one. And then this is which is minus the sine so which means that it's minus 6 cosine theta sine theta plus 6 sine cubed theta cosine theta plus this and the sine to the power 4 of theta. Okay. Right, so you have exactly this. You have exactly this. So there's a 1. Which is 2 sine to the power 4 of theta. Which is minus, now this minus 2 of this. So you can actually expand that. Check this carefully. So if you have cosine of 4x plus I, the sine of 4x is the cosine of x plus I, the sine of x to the 4th power. Let's expand this. It is cosine to the power 4 of x by 1, 1, 2, 1, 1, 3, 3, 1, 1, 1 plus 3 is 4, 3 plus 3 is 6, 4, 1, 1. So you're going to have 4 cosine cubed x I sine x plus 6 cosine squared x I sine x 4 cosine x I sine x cubed. And then you have I, the sine to the 4th power of x. Which means that whenever you have cosine 4x plus I, the sine of 4x, is the cosine of this. Yeah, breaking down the bracket is the binomial theorem. The binomial theorem. And then we use Pascal's triangle for the coefficients to be faster. Pascal's triangle. Pascal's triangle, you start with 1, 1. And then you add up. Okay. I'm here to spend time on the binomial theorem. So you choose the terms. You choose the ones without I. This is without I. Okay, but we need to first write out a little bit more. Which is plus I 4 cosine cubed x, the sine of x, minus 6 cosine squared sine squared, minus I 4 cosine x sine cubed x, plus the sine to the power 4 of x. So that now when you have cosine plus I sine, which is cosine to the power 4 of x, minus 6 cosine squared sine squared, plus sine to the power 4 of x, which is 4 cosine cubed sine x. There's I also here, which is minus 4 cosine x sine cubed of x. Which is cosine that minus 6 cosine squared x sine squared x and that. Now we're dealing with the cosine, so it's this one. But this cosine now, this is the binomial theorem. I'm here to spend time on it because it's like the binomial series we've been doing. So I'm just using the binomial theorem to open the bracket here. Okay, and it's like the binomial series, but the coefficients come from the Pascal's triangle. Like it's 1, 4, 6, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Now, this is the answer they've given for cosine 4x, but yeah, this is what we have got. So you need to make it the same. But the answer given here is in terms of sine only, so you must convert everything here. And then you square this, which is sine squared x plus cosine squared x, which means cosine squared x is 1 minus sine squared x, which is 1 minus sine squared x. Sine squared x plus sine to the power 4 of x. Which is this. Which is 6 sine squared plus 6. And then this one is sine to the power 4 of x. Yeah, so this is work in progress. This cosine 4x is the cosine squared. Cosine squared is 1 minus 1 minus sine squared minus 6 sine squared x plus 6 sine to the power 4 of x sine to the power 4 of x. So now you expand this one. 1 minus 2 sine squared x plus sine to the power 4 of x minus 6 sine squared x. Now, if you add the 6 and the sine squared, the 6 sine to the power 4 and the sine to the power 4 is plus 7 sine to the power 4 of x. Okay, and therefore now the 7 and the 1 sine to the power 4 is 8. The sine to the power 4 of x. And then you have minus 6 sine squared minus 2 sine squared is minus 8. Minus 8 sine squared x plus 1. And this is the answer. Okay, how would we do this? The binomial theorem is clear. Okay, what is the binomial theorem? The binomial theorem states that now if you have x plus y, you want to raise it to the power n. By the binomial theorem, it is the binomial k equals 0 to n. N choose k, x to the n minus k, y to the power k. And then it is the same as you start with x to the power n, y to the power 0. And then to write the rest of these coefficients, but just that obviously it's going to have some binomial coefficients. Let me use a nice example. A nice example would be a cube, like x plus y to the power 3. So if that is the case, you do 1, 1, 2, 1, 1, 3, 3, 1, 1. So you do this one. You raise it to the cube. So by the binomial theorem, it becomes x, you write x cubed, y to the power 0. Then x, you decrease the powers of x by 1, and then you get a 2. Then the powers of the y increase by 1. Then you have x, the powers of x decrease by 1. And then the powers of y increase by 1. And then the powers of y decrease by 1, and the powers of y increase by 1. Then you look at the Pascal's triangle, you take, so this is 1 coefficient, 3, 3, 1. Which means you have x plus y, which is x cubed, then we have 3x squared y, 3xy squared, y cubed. So this is the binomial theorem. And we use the same when we do the binomial series. But this is called the binomial theorem. We use the binomial theorem to expand, but the coefficients quickly come from there. Right, or alternatively, obviously, you can get the coefficients from the binomial coefficients. But the binomial coefficients take a lot of time, but this pattern is very easy. You just take 1, 3, 3, 1, and then just put here. And this 1, 3, 3, 1, this thing is called Pascal's triangle. It's called Pascal's triangle. All right. So now let us do one more. Let us do the sine 4x. The sine 4x. So sine 4x, let's see. Sine 4x is going to be exactly this. So sine 4x is the imaginary part, which is actually equal to this. So sine 4x, you write like this. You write sine 4x from the binomial expansion. Sine 4x is going to become what? So this cosine is equal to this. The sine 4x is equal to this. So the sine 4x is 4 cosine cubed. is 4 cosine cubed x. So the sign for x is 4 cosine cubed x sine x sine x minus 4 cosine x sine cubed x minus 4 cosine x sine cubed x minus 4 cosine x sine cubed x. Then you check this one. So there is this, but you must just deal with some of these here, because if you pull out the sign, you have exactly that. Okay, so if you deal with the sign for x, need to check this out, but you see they have 8 and 4 there. If you pull out sine x, it becomes 4 cosine cubed x. You pull out this one, you become this one, and then we have sine squared x. Well, I want to show prove this one. So this one we have taken it from the binomial expansion, which is sine x. 4 cosine cubed x minus 4 cosine x. The sine squared, you know that sine squared x plus cosine squared x is 1, which means therefore that sine squared x is 1 minus cosine squared x. 1 minus cosine squared x. Sine x, which is 4 cosine cubed x minus. So this one is minus 4. Multiply this is minus 4 cosine x plus 4 cosine cubed. Which is 8 minus 4 cosine x. Right. This is the answer. Okay, that was problem 7. Exercise 7. Then we're going to do exercise 8 now. Let's check exercise 8. Exercise 8 is about the roots. So let us deal with the roots. Find all complex solutions of the following equations. Now, in A, we have, for example, z cubed is minus 1 plus I. So you must do this with minus 1 plus I. So you first do the argand diagram here. Right, so you must first do the argand diagram. X is minus 1 and Y is I. You are here. And therefore, by Pythagoras theorem, minus 1 plus I, we have minus 1 squared plus 1 squared, which is the square root of 2. Right, so now the solutions to this are actually, these can be written as R cosine theta plus I sine theta. The radius is the square root of 2. And then this one is pi over 4, 3 pi over 4. Which is 3 pi over 4. Okay. So we're going to do z cubed. Okay, then we're going to add 2k pi. The sign of 3 pi over 4 plus 2k pi. Then you have the z. And this is going to be this raised to 1/3. Yeah, the angle is, you do the Pythagoras to get the r. Then the angle, you use the tan theta. Is y over x. Y is, this is like x and y. Y is 1, x is minus 1. All right. So if this is the case, then you're going to do the tan is -1, but you must do tan theta is 1. Reference angle, which is arctan 1. Pi over 4 radians. Okay, do pi over 4 radians, but now then this is pi. So what must this angle be? So you must say pi minus pi over 4. Then it is 3 pi over 4. So this angle is 3 pi over 4. You call it theta. This is the angle. You put it there. After this, after putting the angle there, you continue with this. You continue with this, and then you add 2k pi. 2k pi, always add 2k pi. And then now when you take the root, the cube root, because this is like z to the power 3, now you solve for z. You raise it to the power 1/3. So this is going to be the cosine of 3 pi over 4, 2k pi, 3 pi over 4, 2k pi divided by 3. Divided by 3. So which is 2 to the power 1 over 6. To multiply, this is 3 pi plus 8k pi divided by 12 plus I, the sine of, or you can write it like, yeah, you just need to simplify it. So to simplify it, we have the following, yeah? Divide by 3 here, which is exactly pi over 4. Plus 2k pi divided by 3. I, the sine of pi over 4 plus 2k pi over 3, which is exactly this. Okay, this is for finding the, because it's z to the power 3, you're finding the cube roots. You're finding the cube roots of this number. Minus 1 plus I, cube roots of that complex number. Okay, but the cube roots are valid for what? For 3 values of k, 0, 1, 2. Because those are the cube roots. So you have 0, 1, 2, those are the cube roots. 0, 1, 2, those are the cube roots. 0, 1, 2, they become the cube roots. So then we continue. We continue. We continue. Right. Right. Continue. Right. We continue. Okay, I lost you. Now we're dealing with part B. Z to the power 4 of minus 1, which is the real part of that. Okay, then the angle is pi. Okay, so every complex number the minus 1 can also always be written as what? Cosine theta plus I sine theta. And then you'd have the, when you take R, you take the modulus of this. The modulus of minus 1 is minus 1 plus 0I. Is this squared plus 0 squared, which is 1. Cosine of theta, which is pi plus I, the sine of pi. Then now you solve for that. Okay. So if you solve for z, then it becomes the cosine of pi plus 2k pi out of 4 plus I, the sine of pi plus 2k pi. Like this. And therefore, these are the fourth roots. So for the fourth roots, k must be 0, 1, 2, 3. Okay, now if k is 0, let me see what you're saying here. Yeah, the z exponent. Yeah, this z exponent now is for the fourth roots, because now when you take the fourth root, when you come here, you must remove it, this exponent of that. So when you remove it, you raise 1/4 and you raise this to 1/4. Because now you want to solve for that. When you raise it to 1/4, it cancels here, and then you're gonna be having the power 1/4, which becomes this. Because to the angle, you always add the multiples of the period, which is 360 degrees by k. 360 degrees by k, and then you divide by 4. But now when k is 0, z is cosine plus I, the sine of pi over 4. 1 over the square root of 2, 1 over the square root of 2. You put k equals 0 here. Okay, yeah, then you would get the rest of the answers to this. But you can leave your answer here, because then at this point, you need to find all the complex solutions. These are the complex solutions. These become the complex what? These become the complex solutions. They become the complex solutions. The rest of the things are the same, like same thing, same. Now the E, you need to use the quadratic formula, So in E, for instance, you have z squared plus z plus 1 equals 0. How do you solve for z here? Use the quadratic formula. Z is minus b plus or minus the square root of b squared minus 4ac. You divide by 2a, which is minus 1 plus or minus the square root of 1 minus 1 divided by 2 by 1, which is minus 1 plus or minus square root of minus 3 is the square root of 3i divided by 2. So we continue. We continue. But then in the end, you have this. Right, because you need to find out the complete, and this is the answer. Okay, and then this one also, you can do this one F. So I use the quadratic formula for this. Quadratic formula. Now for F, use the quadratic formula also, because this is biquadratic. Biquadratic equation. Z to the fourth power, z squared plus 1 equals 0. Minus b plus or minus square root of b squared minus 4ac over 2a, which is minus 1 plus or minus the square root of b squared minus 4a c over 2a, which is minus 1 plus the square root of minus 3 divided by, what is the square root of minus 3? It's the square root of 3i divided by 2, but this is z squared now, because this one is z to the fourth power, but you can write it as z squared plus z squared plus 1 equals 0. At this point, you can let be w. W squared plus w plus 1 equals 0. So that now this is quadratic, and then use the quadratic formula. At this point, now you have this z squared minus 1 plus or minus square root of 3 I divided by 2. So when you take the z, it's going to be plus or minus the square root of minus 1 plus or minus square root of 3 I divided by 2. That sort of becomes the answer there. That becomes the answer. Okay. So the rest of the things are the same. The rest of the things are exactly the same. Okay, I think that we can take a break. We'll come back. But I know that you're anxious because now it's just like 9:30. We can take a break for 1 hour. Then I'm going to send you this recording on the complex numbers, yeah? Yeah, I know. Okay, let's just go to the complex functions. Okay, this is start 12. Yeah, then we're going to recap on start 11. But now I want us to go to the complex functions. There are elementary complex functions that we need to discuss. Okay, some of these you already know, and they're not different, like exponential z. Exponential z is the same as 1 plus z squared over 2 factorial, z cubed over 3 factorial, and so on. So this is the exponential z, but it is always the same as z to the power k over k factorial k0 to infinity. So this is the exponential z. Okay. Now let us do some exercises on the exponential functions. Let us find the log of this. So to find the log of 1 minus I, you must first use the Argand diagram for this. Okay, you must first use the Argand diagram, and then you plot 1 minus I. Right, so you continue. So then you have this, which is the square root of 2. Square root of 2, this angle is minus pi over 4. The tan of theta is y over x. And then y is minus 1 for this one. Imaginary z of real z. So y is minus 1, x is 1. Arctan of 1 is pi over 4 regions, but you can do the minus 1, and then it's going to be minus pi over 4. So which means that 1 minus I is r. So to get this log of this, you get the log of 1 minus I. You start with the 1 minus I, and it must be r cosine theta plus I sine theta. What is the r? R is this one. To get r, you take this number. You take its modulus, 1 minus I, is square root of 2, which is the square root of 2, and then you have the cosine. The angle here is minus pi over 4, but you can take it as what? You can go like this. You can say 2 pi minus pi over 4. 4 pi 2 pi is 8 pi minus pi is 7 pi over 4. So you have 7 pi over 4, which is 7 pi over 4. I, the sine of 7 pi over 4. Seven pi over 4. So that in the end, we take the log. So the log of 1 minus that is the log of this. So the log of this is the log of the square root of 2. But this thing is normally written as the square root of 2e to the I 7 pi over 4 plus 2k pi. So this 1 minus square root of 1 minus I is e to the I 7 pi over 4 plus 2k pi, which is 1 minus I. So you have it becomes the ln of the square root of 2 plus I. Then you bring down the 7 pi over 4 plus 2k pi. K in that. So this is the answer to this. So, but you can also do this one. So now the complex number in rectangular form can be written in exponential form using Euler's formula. So this becomes exponential form. 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 This That becomes the exponential form. Okay. That becomes exactly the exponential form. Right. Okay. So we continue. We continue. We continue. Any question on this? Any question on that? Any question on these? Right. Any question on that? Okay, so now let us look at part B. Right, part B would be you must first draw the argand diagram. And then you have -2. And then you're going to measure this angle here. To get this angle, then you need to use arctan theta. Or rather, tan theta is y over x. So if z is -2i, so 0 minus 2i, which is y is -2x is 0. So that in the end, when it's undefined like this, it means the angle is sitting here, but this angle you already know is 3 pi over 2. 0, pi over 2, pi. So if you have -2i, then you must take the modulus of this number, which is 2. So this must be r e to the I theta. Always we use that one for the log. The radius is the modulus, which is 2 e to the I. The angle theta is 3 pi over 2 plus 2k pi. Right, so you then be in a position to take the log of this. So you have this one, and the log of this, it becomes the ln of 2. Then you bring this one down. 3 pi over 2 plus 2k pi, k in z, which is the answer to this one. With the argument 3 pi over 2 radians, which is sitting here, or just 270 degrees, but obviously we're not using degrees, we use radians, okay? That is something that you can take note of about the complex functions. Let us find all solutions of this one in exercise 5. If you have the exponential of z equals -2, what we do here, we have the exponential of z. So it's like e to the power z is -2. So use the log. So you can take the log of e to the power z equals the log of -2, which means z is the log of -2. Let us check the log. Okay. Which means that z equals the log of -2. So now you have this angle, which means that theta is equal to pi radians. Every time if you have a complex number like this, you write e to the power z is -2, e to the power z, but -2 multiplied as r e to the I theta. What is the radius of this? So you take the modulus of -2, you get 2. This one is pi plus 2k pi. Which is ln 2 plus I pi 2k pi. Okay, so now pi 1 plus 2k, k in that. So this is the answer. This is the answer. So you can write the one on the right of the division. You can write the one on the right of the division. And write the one on the division. Let us look at the next one. Looking at e to the power, the exponential of 3z equals 1. It's like e to the power 3z. But you see, the 1 can be written as r e to the I theta. Any number can be written, any complex number can be written like this. So the 1 can be written as r e to the I theta. But you see, you take the modulus of 1, you get a 1. Zero. The angle is 0, but the modulus is 1. This is r. So e to the 3z. 0 plus 2k pi. K in z, which means 3z is I 2k pi. K in z. We divide by 3 out of this, which means z is, you always add 2k pi. Always is it's like the period is 2 pi is 360 degrees of the sine and the cosine function. So you divide by 3 here, it is 2k pi, you divide by 3. K in z. K in z. So this is the result of the exponential function. Okay. Then let us do more of this. But now this one is the argand diagram. Imaginary z, real z. Okay. So it's the same thing here. So it's the same thing there. So you write it like to the power 3. So what you have. Okay, now writing this to the power 3 can also be written in the log. If z is an integer and wz is any value, for example, this, fine, but this one is optional. Optional that. Yeah, so this one is very important. You can consider this one, just practice with this one here. So when you have I to the power 1 plus I, it is e to the power the log of I to the power 1 plus I. E to the power 1 plus I, the log of I. What is the log of I? To get the log of I, you must write I is r e to the I theta. So imaginary z, real z. So if I is here, do this here, theta is pi over 2 radians. The modulus of I is 1, which is 1 e to the I. The angle theta is pi over 2 plus 2k pi. Right, so if you have the log, it is the log e to the I pi over 2 2k pi, which means the log of I is the same as the ln of 1 plus I pi over 2 pi over 2 plus 2k pi, which is e to the 1 plus I, the log of this, which is ln 1 plus I plus 2k pi. E to the 1 plus I. Okay, the ln of 1 is 0, giving us I plus 2k pi. So you multiply everything at the top. So the I and the I is minus pi over 2, 2k pi. And then e to the I pi over 2, 2k pi. All right, so plus 2k pi. And then now you have these other things. And this e to the I, this, you used Euler. E to the I theta is always cosine theta plus I sine theta, then you use that. And therefore, if you use that, you're able to get this answer here. You're able to get this answer there, and this has infinitely many solutions in terms of K. And then now, we're going to do exercise 6. Exercise 6. What is exercise 6? So when you have minus 1 plus I, it is e to the log minus 1 plus I to the I. E to the I, the log of minus 1 plus I. Okay, so always when you have the exponential things like this, you write them like this, because in mathematics, e to the log of z is the same as z. So e to the z to the power I like this is like this. e to the log of z to the power I is z to the power I. So you have this. But if you take the modulus of minus r1 plus I is the square root of 2, which means I, which is the log of this. Now, a complex number like this is always r e to the I theta. So the log, what is the radius? The radius is actually exactly the square root of 2e to the I. If this is the case, x is minus 1, I is this, and you have this. So that argument is that. But if this is pi over 4 radians, this one is 3 pi over 4. How do we know? Because tan theta is y over x. Y is that, which is minus 1. Theta is minus pi over 4. But this one is 3 pi over 4 because this is pi over 4. So you do 3 pi over 4 plus 2k pi. Okay. So this is what we have. So this is the same as I. And then here you're going to have ln of the square root of 2 plus I 3 pi over 4 plus 2k pi. E to the I square root of 2 minus 3 pi over 4 plus 2k pi. Which is 3 pi over 4 minus 2k pi. E to the I, the ln of the square root of 2, which is e to the minus 3 pi over 4 minus 2k pi, which is the cosine of the ln of the square root of 2 plus I, the sine of the ln of the square root of 2. K in that. And therefore, this becomes the answer. Right. Now the time is exactly 11 p.m. We have run for nearly 3 hours. Just speaking about the complex things for nearly 3 hours. So we're going to take a break and then come back and do Part 11. I need to take a break, I think, for 1 hour, 1 hour break. 1 hour break, and then we return to Part 11. And we return and do Part 11. And then we can recap on the complex and see what is missing. But also, when we return, we're going to do Part 11. But let's take a break and refresh a little bit, and then be back in 1 hour. It's 11 o'clock now. We'll be back at 12. Right. So thanks for now. I'm going to send the recording in the next couple of minutes. Okay, thank you for joining us. I'll see you again at 12. I'll try not to sleep, obviously, because of the test and things. Yeah, okay. See you in 1 hour, but I'll send the recording just now. Thanks, dear. Goodbye for now. Bye. Yes. You must know these formulas, all of them. You must know these formulas, all of them, to solve all these exercises on the complex numbers. You must know all the formulas. But once again, it was just a run on the things. Now we're just running through the things, but we shall have a recap on it. Yeah, shall recap on this with Part 11 when we come back. But let me send the recording of this, then we shall return in 1 hour. But I'm going to send the recording just in the next couple of minutes. Okay, thanks, dear, for now. Okay, let's relax a bit and come back. Thanks, then. Goodbye.